Hi, so I wanted to talk to you again about the supercapacitor. Now, here it is. That is 0.08 of a gram, and it's 1 centimetre by 1 centimetre, and it's 4 microns thick, and it's actually 2.3 farads. Now, in order to make that, you're going to need to stretch yourself a little bit, but it's very, very makeable. Now, the video is going to be a bit talky because I'm going to talk you through the steps as opposed to demonstrate them. The reason for that is if you want to know exactly how to do everything that you need in order to make a supercapacitor like that, all of the videos have already been done and are on the site. Just have a look at them. Go through the graphene videos to learn how to make graphene. Go through the ink videos to learn how to make ink. Go through the early capacitor videos to learn what capacitor is all about and why I'm doing this stuff. And then you'll understand and be able to reproduce that yourself. But like I said, it takes a little bit of a stretch. Now what we're aiming for here is an ultralight supercapacitor because we want to be able to roll that up or lay that out in flat sheets and make something astonishing. Now that being 2.3 farads is in itself astonishing. What that means is it's about 3.5 times better than the currently available commercial supercapacitor. So here is a currently available commercial supercapacitor that's 2.7 volts and 500 farads. You can see it's about the size of a D cell. There's a D cell for comparison. What that means is that if I make that same size supercapacitor from the capacitor I'm just about to go through, then that will have a capacitance of in the order of 1,700 farads, something like that. So we're looking at 1,700 farads in that size of capacitor. Now, because we're looking for thin, the most important thing we need are thin plates that will do the job, and the first thing we need is a current collector plate. Now, I'm not suggesting you go and get something and sputter it with aluminium because you don't need to, because it's readily available. And here it is. This is printer's stock. We actually print labels from this stuff for putting onto paint cans. It's sputtered aluminium on one side, on polypropylene. Very thin, it weighs next to nothing. The coating of aluminium on there is in the order of 100 micrometers or so. It's an extraordinarily thin coating. It brings its own challenges because the first step that you need to do with that is etch the surface. And you can't etch the surface by taking a bit of wire wool to it because in no seconds flat you'll have gone straight through the aluminium and have the white polypropylene showing up through the underside. So what you need to do is etch it with an etching solution. This etching solution is copper sulfate and sodium chloride 50-50 mix and in a litre of water. And it's pretty strong in this form. It's a bit too strong for that. If I take a cotton wool ball, swab it on with this, wipe it over that plate, it will eat through the plate really, really quickly. So what I need to do is water it down and do a few tests until I get that thin black layer, that when that thin black layer washes off, I'm left with bright aluminium underneath it. It'll look bright, but it's actually etched, and we'll get a nano-etched aluminium surface ready to accept our active material. Now, our active material, remember, is just graphene. If you want to know how to make it, look at the graphene videos. Once you've made the active material, you then have to turn it into an ink, which basically means mixing it with water and some kind of binder. In my case, I've used polyvinyl pyridine for this one, but you can use polyvinyl acetate quite happily. There's quite a lot of binders you can use, but you mix it with the binder. Now, the binder I used, because it's PVP, I only use 3.5%. PVA uses about 10% by weight of binder to the active material. So you just make your active material and make it up into an ink. You can have a number of ways of applying it. Now, I did stuff on spin casting, so you can spin cast it if you like. Personally, for large sheets, spin casting is a bit difficult, so I made mine up into an ink and put it into this thing. And this is for an airbrush, because I happen to have an airbrush. I made it into an airbrush applicable ink. And there's the airbrush there. Once it's actually as an airbrush ink in my airbrush, then I can control that just by spraying over a number of coats, making the coat thinner and going over it quite a few times. And after I've done that quite a few times, what I end up with is this, which is a stupidly thin sheet of polypropylene with an etched aluminium collector and a graphene layer adhered to that etched aluminium surface. And that is my active material for my supercapacitor. Now, that supercapacitor is actually nearly ready to be made because that is mostly what it's all about. All I really need is a separator and then some electrolyte. Now, the separator is a problem in itself. Buying a separator, commercial separator, is quite difficult. But it's quite easy to get hold of some. Just get a dead battery, saw it in half, unroll it, and you get some polypropylene separator right there. Give it a wash, and you're ready to roll. Or you can make it yourself. Now, I make my own, and I make it by drop casting a separator-based material in a solvent. I add more solvent if I want it thinner, less solvent if I want it thicker, then just leave it on a bit of glass until it dries, and cut out the size of separator I want. Again, if you want to see experiments on that, there are previous videos where I show you how to do exactly that. So you get your separator, you get your plates, and you cut the size you wanted. And I cut 1 centimetre by 1 centimetre because most of these things are done in that kind of test size. So there's my test size, and I put out a little bit of sellotape, put everything on the sellotape, folded the sellotape over and snipped it so that I got my test cell, giving me a couple of tabs I can connect to, a little gap here for my electrolyte. Now the electrolyte I'm using is just salt water, it's sodium chloride. I'm using that because it's perfectly safe. It's not the best electrolyte. It'll limit you to about 1.2 volts. If I use an ionic solvent, ionic fluid in this, I get limited to about 2.7 volts, something like that. And all I do is put it in a needle bottle, squeeze the needle bottle between the little gaps, a couple of drops, and then set it to one side for the whole thing to soak through. And that's my finished supercapacitor. Now, I discharged this thing over a 1 ohm resistor initially, and I counted 2-3 seconds. I wasn't sure how many seconds I counted, and I thought, how many seconds was that? Now I did it over that because for every 1 second that you count that, it's actually 1 farad. But then I discharged it over a 10 ohm, 10k resistor, and worked out that it was in fact 2.3 farads. So we got 2.3 farads in that ridiculously small thing. Now, I have learned from doing YouTube videos that it's not possible to please everybody all of the time. Some people are without a doubt going to write and say, that's just a talky video, why don't you teach us how to do it step by step? Well, the reason I don't teach you how to do it step by step is because I've already done that. Have a look at the videos that teach you how to do all of the separate things. This one's about putting them together. Other people say, hey, are you only doing this because you're running out of ideas? And I think, oh, good Lord. Because on the one hand, of course, if you just do idea after idea, the criticism you get is, hey, you never finish anything. If you go towards finishing something, the criticism you get is, hey, you're running out of ideas. So there's no pleasing everybody all of the time. But this video is all about pulling this stuff all together so that you can see what kind of results we're actually getting from the previous videos we've done on how to make this stuff. So again, if you want to know how to make this stuff, review the previous videos where I tell you. If you want to see what happens when you put all this stuff together, then you end up with something that's 3.5 times better than the commercial product, and something that size is 2.3 farads, which means when we make that sheet and roll it up into that size, we're going to get 1700 farads. So that's the next thing to do, is I'm going to make a can like that and measure its capacitance, and I'm expecting something like 1700 farads from these processes we've been going through. So I hope that was of interest to you, and thank you very much for watching.